devices was designed but could not be built only until recently. And it works, just as Babbage designed it. Every turn of the engine's driving handle is carried through gears, cams, rods, levers, and springs to release and arrest precisely aligned number wheels. The helical arrangement of the steel fingers continually pulls the register towers to find and perform the carryings of tens. Now, since all computation requires much effort, it is natural to ask, how fast can we arrive to the required result? The answer to this question lies in the study of complexity. It turns out that not all computational problems have the same complexity. Some are easier to solve than others. For some problems, people have been able to find very fast algorithms. But for other problems, the solutions that have been found are incredibly slow. Now let's take a look at an old family of algorithms, the sorting algorithms. Have you ever been to an algorithm race? I'll take you to the racetrack. Follow me. The competitors are the sorting algorithms, those algorithms that have been devised to sort a file, namely insertion sort, selection sort, bubble sort, shell sort, merge sort, heap sort, quick sort, and quick sort with a median of 3 modification. The racetracks are the initial conditions for the algorithms. The basic one is a randomly ordered file, and we just see how well each algorithm performs in sorting a randomly ordered entry or input. We also have some other kinds of tracks: the nearly sorted, the reversed order, and few unique keys. In all these cases, some algorithms perform differently. But now let's look at one particular race, the random track. So, ready? Go! Now we see the progress of each algorithm, and as we get close to the end, we can clearly see that heap sort, shell sort, merge sort, and the quick sorts were the fastest ones. We would like to express the performance of an algorithm as a formula, where y would represent the number of steps required to finish the algorithm, and n would be the input size. In the case of the sorting algorithms, the number of records to be sorted. We say that the algorithm runs in polynomial time when the running time is bounded or smaller than or equal to a proportionality constant times the input size raised to an exponent. This formula represents all a polynomial time. Polynomial time really marks the boundary between all those problems that are considered practically solvable, those in this shaded area called the feasible problems, those that are likely to be solved within our lifetimes. For any other problems like these ones, even if they have a solution, the algorithms would take too long a time to be of any practical interest. This table lets us perceive what we mean by practicality a little better. This table was made on the following basis. We assume that we are using a processor performing 1,000,000 high-level instructions per second. And in cases where the running time exceeds 10 to the 25 years, that's what we mean when we say it takes a very long time. So if the algorithm has a running time of n, linear running time, or n log n, or n square, or n cube, or this kind of exponential growth, or 2 to the n, it might seem that there is not a big difference between this exponential and this exponential time. And this is the largest and fastest growing function or growth function that we will ever encounter, the n factorial. If the input size is 10, then the running time, if the running time is linear or n log n or n square, whatever, it will take less than 1 second, except when we have a running time of m given by n factorial, in which case it would take 4 seconds. If we have a modest increment in the input size from 10 to 30, then the running times between for algorithms running in linear, n log n, n square, and n cube, and this modest exponential keep under 1 second, whereas this one has increased to 10 minutes, and the factorial is now 10 to the 25 years. Yes, a 1 with 25 zeros after. And if the input size is 50, then the range of practicality, which is let's say times under 1 second, extends only to a polynomial of degree 3, because exponential times start becoming very long. And if the input size is 100, then that range gets reduced even more dramatically and drastically. And 100 is a very small size. You can say that any problem of size with an input size of 100 is a toy problem. In real life, it's easy to find problem inputs with input sizes of 1,000 or 10,000, 100,000, or even on the millions. And if you see, when we have an input size of 1 million, then the only practical running times are the linear time, taking still under 1 second, and the n log n, about 20 seconds, but even a modest polynomial growth would take 12 days. For many non-trivial problems, there is a natural brute force search algorithm that checks every possible solution. For example, in the case of stable matching, we would first need to generate all possible matching lists, and this would imply n factorial, since we would have to pair all boys in a given order with any of the n factorial permutations of the set of girls. And then afterwards, we would need to check all pairings of assigned couples to see if they are stable. And it would be this number, n choose 2, or n factorial over n minus 2 factorial which is equal to this quantity. Then in the end, the total number of checks we have to do is n times n minus 1 over 2 times n factorial. And this is the total number of checks. And for the sorting problem, the brute force approach would imply n factorial steps, since we would have to check all permutations of all the file's elements.
Come on, kid, do it! He did it! He did it! He got the 710, Randy! Oh my God!
The worst case analysis is just placing a bound on the largest possible running time of an algorithm on an input of a given size n. This generally captures the efficiency in practice, tells us how efficient an algorithm can be. It might be a little too conservative, too draconian a view, but it is hard to find an effective alternative. For example, in the case of stable matching, the worst case is about n squared because that is the maximum number of proposals that we may get, and that number can be refined a little better. And in the sorting algorithms, speaking of comparison-based sorting methods, the bound is n log n for the worst case. As for the average case analysis, that is a bound on the running time of an algorithm based on a random input as a function of an input of size n. Now, it has many caveats. The first of those is that it is hard, but it is, if not impossible, to accurately model the real instances by random distributions. That is, the input can come in any way, and it is hard for us to find out what statistical distribution would fit that kind of input. And then if we tune this algorithm for a particular kind of input, it would perform poorly on other inputs. But perhaps the worst property of an average case analysis is that it tells us more about the nature of the input than about the algorithm itself. To describe the asymptotic order of growth of an algorithm, we introduce a notation involving a function t of n, which is the time to execute in terms of the number of steps or units of time for an algorithm that we are interested in studying. So n is the argument for this function, is the size of the input for the algorithm, the number of records that we want to sort, the number of boys and girls that we want to match, the size of the input. And we have on the right hand side this big O notation, which will be explained better a little later, but right now it just means that it is an upper bound. Whatever is inside the brackets is an upper bound. And this function f of n is a simple function that denotes the class of growth. So in the case of upper bounds, we say that a function t of n is big O of f of n, or is of the order of f of n, if there exist constants, which are called c, a positive one, c greater than 0, and n naught, also greater than or equal to 0, then such that for all n bigger than n naught, we have this relation holding t of n less than or equal the constant times f of n, then we say that t of n is big O of f of n. Here we have t of n, which is this specific polynomial, growing slower than the n squared multiplied by a constant. And this happens here. Let's take a look at this diagram. In this case, in this figure, the red line, the red curve, represents the specific polynomial, 47n squared minus 329n plus 7003. And the dashed line is the polynomial n squared multiplied by a constant. In this case, the constant has the value 58.4. And the statement tells us that it needs to hold that the growth of the red curve must be below the growth of the blue curve after a given point that we call n naught. That's what the n naught constant means. There is a point afterwards which this relation holds. Okay, And we can see that the values for the constants can be several. We have several solutions. For example, we can with this slider we can change the value of the multiplier, and you see that the multiplier for n squared has changed from 58.3 or something to, we can change it to 71, and we still have the dashed curve being on top of the red curve after a given point in the x-axis, and this constant n naught can also be changed. So we can say also that for n naught equal to 30 and c equal to 71.7, the growth of n squared multiplied times the constant will be bigger than the growth of the red polynomial, or the red curve that represents the reference polynomial. Okay, so t of n is big O of n squared. That's correct. By a similar reasoning, we can find constants c and n naught such that we would have the same polynomial t of n being big O of n cubed, because n cubed grows even faster than n squared. But is t of n big O of n? So in other words, can we put an upper bound for this function which grows like a quadratic? It is actually a quadratic. Can we bind it by a linear function? And we see that it is not possible. To see that the polynomial is not bounded by a linear curve, a linear polynomial, we have changed the dashed line in this new diagram. In this plot, the dashed line is now a straight line, a linear function, and it is supposed to bound the red line, which is a polynomial 47n squared minus 329n plus 7003. Now we see that if we fix a multiplier, like in this case 1890, then we have two inflection points, one to the left and one to the right. I mean, 2 points where both of the lines cross, and in that interval the blue dashed line is indeed a bound, or is above the red line, but there is a point sooner or later after which the situation will be reversed. So the dashed line will not be an upper bound for the red line, and that will happen if no matter how I change the value for the multiplier, I would always have these two crossing points, especially the one on the right. And as for n naught, well, there's no value after, if we fix n naught big enough, let's say in this zone, so that the dashed line is above the red line, we know that this situation will not persist. And even if we move the dashed line, we see that it will, even if we move it to some other place, we know that we will have a crossing point at some time, and then after that we wouldn't be able to bind the polynomial with a linear function. We can define lower bounds in the same way as we define the upper bounds. Only this time we will use a slightly new notation. Instead of big O, we will use a big omega to denote a lower bound. And the sense of the inequality in the definition will be changed to greater than or equal, which means that the bound, that the dashed line will have to be below the red line. In this example, we see that for the values of the constants that we are observing here, the conditions for the definition hold because the dashed line is below the red line, which means the dashed line is a lower bound for the red line, and the red line is the polynomial of reference. And these constants can be changed, but it doesn't change the fact. Since we can find at least one set of values for those constants in which the condition above holds, we say that in this case t of n would be big O of n squared. So the polynomial for its 47 n squared minus 329n plus 7003 is big omega of n squared. And we can find a similar argument to say that this same polynomial is bounded by a linear function. So we have t of n is big omega of n squared, and also t of n is big omega of n. But is t of n big omega of n cubed? Is n cubed a lower bound for t of n? And we would see that it is not the case. We can also define a tight bound. A tight bound is at the same time an upper bound and a lower bound, and we can define it in the following way: as the limit when n tends to infinity of f of n divided by g of n. If that happens, we see that f of n will be bound by g of n tightly, or in other words, g of n would be a tight bound for f of n. For example, in this case, we have that the polynomial 47n squared minus 329n plus 7003 is big theta of n squared, because we can divide the polynomial by the proposed bound and take the limit when n grows to infinity, and we see that these terms, these two n squares can cancel, and we would get this expression derived from the previous one, which reduces to 47, and 47 is greater than 0, so there is a limit, and it is a positive limit. So in this case, yes, n squared is a tight bound for 47n squared minus 329n plus 7003, and that means that it is also at the same time an upper bound and a lower bound. So that's what we see here. Now we have the definitions for upper bounds, lower bounds, and tight bounds being similar and based mainly on the sense of this inequality, but the concept is the same that has been explained. Except for the tight bound. The tight bound, the best way to understand a tight bound is using the limit definition. Now, this notation is very old, and it's really an abuse of notation because it is in no way an equality at all. This symbol is misused, and it is asymmetric. If we have f of n equal to 5n cubed and g of n equal to 3n squared, so we have a cubic polynomial and a quadratic polynomial, we clearly see that f of n is big O of n cubed. But if we could simply use it as an equality, we could substitute g of n on the right hand side because of we assume that it is an equality, and then we arrive to an incorrect conclusion. So a better notation for the big O of n would be to use or to substitute the equality sign by the inclusion sign, by the membership sign, the set membership sign, because in this way we are indicating the idea that this function belongs to a class of functions that grow in a way that is bounded by f of n. This notation, the big O notation or big omega, big theta, has the following properties. Let's say that we have that f, a function, is big O of g and g is big O of h. Then we can conclude safely that f is big O of h. So there is a transitivity, a transitive relation that is held equally by the big theta and the big theta and big omega notations. They are also additive. If we have that f is big O of h and g is big O of h, then f plus g, the function f plus g, will also be big O of h. And a similar case can be made for big omega and big theta. Let's check some asymptotic bounds for some common functions. Whenever you see a polynomial, which is an expression like this one, a constant a0 plus a1 times n plus a2 times n squared plus a so on until ad times n to the d is a polynomial of degree d. This polynomial is big theta of n to the d if this coefficient is bigger than 0, which means it's positive. So, and we call that polynomial time. So whenever you see a polynomial, it doesn't matter, you can disregard all the constants and choose the term that has the highest exponent, and this would be the bound, the upper bound or the lower bound or the tight bound in this case. And it would be safe because it is the term that has the highest exponent, so it dominates the growth. Whenever you see an expression like this, big O of logarithm base a of n, you can substitute it for, if it's equal, you can substitute it for big O of logarithm base b of n, which means that it doesn't matter what base you use for the logarithms, since the logarithms with different bases are only a constant away from each other. So we can say also that the logarithmic function is big O of n to the x, because it grows slower than every polynomial. Another important relation that we can use as a rule of thumb is for the exponentials. Whenever you see an expression like this one's, in which r is greater than 1 and d greater than 0, n to the d will be big O of r to the n. So in other words, every exponential grows faster than every polynomial.